Actually, what happens when you increase VDS more than the VOV? Remember that VDS equal to VOV having a pinched off channel at the drain corner, right? Here, right? But if you increase VDS more than VOV, this is the point for this VGS, right? For this VGS, you are having VOV as 2, right? For example, so it means here you have VDS equal to 2. If you increase your VDS greater than 2, then the pinched off channel is the pinching tip is go further back. Why? Because VDS increasing more. Drain to source voltage is more than gate to source voltage, right? So we are having the terminal voltage, the dropping along the channel, the tip is going more towards the source side, right? So this effect is called, now your channel, previously it was L, is now delta L is reduced, channel length is reduced, right? Now your new length as far as the conduction channel is concerned is L minus delta L. Obviously current flows because of the applied voltage, right? High voltage charges will be swept out, right? But this effect is called channel length modulation, and because of this you are having a resistance between drain and source, right? And because of this you are having a slope in ID and VDS, right? As you increase VDS, your channel pinching off effect goes back, length modulated, having a resistance between ID and VDS, current increase but slightly, so it means you are having a slope here. Okay, and this channel length modulation, how to find it, because it is different for different curves, but luckily someone has extended these curves and found out that they are meeting at the single point to some impractical value, but a single point. Now you can use simple algebra or the 2-point form to find the current for that curve, the early effect resistance of that curve, right? So this is called early effect, and it is equal to what? 1 upon lambda. And what is lambda? Lambda is the channel length modulation parameter. Okay, so VA is equal to 1 by lambda, because this value is minus VA for NMOS, so it's equal to minus 1 by lambda. How to incorporate it? Increasing VDS beyond VD saturation. VD saturation is this point for this curve, this point for this curve, and so on, causes the channel pinch off point, thus reduces the effective channel length by delta L, right? By delta L. Then what happens is you are having a slope here, right? And how to find it? Using 2-point formula, this one and this one, because you already know this thing. So by using this formula, you can find the equation of this curve as a linear line here. Now it is behaving linearly, having slope. This not constant linear, but slope, having slope, right? So you can incorporate it, and the whole equation is found to be the previous saturation value but multiply by 1 plus lambda VDS. This formula actually will precisely show you the practical characteristics, right? So this is what the current relation of MOSFET transistor is. How about PNP? As I introduced in the previous slide, you would be having VSG here, right? VSG should be less than VT. VSG less than VTP, because for NMOS it would be VTN, right? VOV is what? So it is better to use a modulus sign here, right? To avoid the ambiguity in the signs and the opposite way of taking potentials, right? Instead of VGS as VSG and instead of VDS as VSD and so on, right? So it would be also modulated. So you can do everything. So you can check the book for PMOS for yourself. Okay, for all these things. It's similar. So now your resistance R naught is 1 by lambda ID or VA by ID. So it's the same. You are having an output resistance in NP in transistor. It was VA by IC or VA plus VCEQ by ID, right? Here it is VA by ID. So before we introduce the resemblance between NMOS and PMOS, let me show you the remaining curve, the remaining graph, this one. We have explained you all these things, right? If you want to revise it, please rewind this video and then see what we have said about this, right? Actually, we have applied the gate voltage more than the source voltage. How much more than? At least greater than VT, right? And how much greater than VT is VGS is your overdrive voltage. VGS is how much greater than VT is your VOV. And if this is happening, it means you are having a channel and you are having a conduction, depending on how much it is, how much VGS you have, right? And then what current you will get, right? It depends on how much VDS you are applied. After selecting the VGS, after applying the VOB, how much VDS you have. So in fact, if you say take the VD and S same, no current. If you increase the VDS, right? If you increase the VDS, you are having a linear relation, then a small curve, and there is a point here where your VDS equals VOV. This is the border of triode and saturation region, right? So here it is also shown here. So this is triode region and this is the saturation. It means this is the limit. At this point, this difference, this VDS should be equal to VOV, and it is shown here, right? This is VOV. So you can see this distance and this distance is the same. So it means this distance and this distance will also be the same. So we can say also about VGD or VDG, right? So it means VGD if greater than VT, then you are in the triode region. And if it is less than VT, you are in the saturation region, right? So anyway, don't need to learn about the difference of VGD to check the mode. It is better to see VGS first. If it is greater than VT, you are having a VOV, and if your VDS is greater than equal to VOV, you are in the saturation region. If it is less than, if VDS is less than VOV, you are in the triode region, right? So if you understood everything about NMOS, right? Apply initially for a small channel does not altered, but later channel altered and a pinch off effect, and then pinch off goes back to have a slope here. Here it is also the early effect neglected to show you just the resemblance. Okay, so in triode region, right, VGD is greater than VTN, so we don't need to remember this. We are going to remember the VDS and VOV and other things, right? If VGS is less than VTN, cut off. If VGS is greater than VTN, VT and VT or VTN, then how much greater is your VOV? And now if your VDS is less than VOV, you are in the triode region. This formula will work, only one formula, right? Why? Because for small VDS, this will be neglected and everything works for even for the linear part. So for the whole triode region, you need to use only this single formula. And or this one, they are both the same. But if you are having VDS greater than equal to VOV, then you are in the saturation region, then current saturates, right? Or equivalently, if you put this as VOV, the VOV square, right? VDS is equal to VOV. So this formula works only at this point. And if you want to use the same formula for the whole saturation region, it means you are neglecting the saturation, early effect. Okay, so anyway, to show you the resemblance between NMOS and PMOS, here early effect is neglected. Okay, so how about PMOS? It is shown here. So in PMOS, because the source is of P type, so it means it would be at the higher potential than gate to have a particular VSG. And similar is the case, Vs should be higher than Vd to set a particular VST. So now suppose if you have source at a particular positive potential, then gate should be lower than the source. How much lower? If it is lower than source but not as much as Vt is, then you are in the cutoff region, right? But if your gate is more lower than S, how much more? More than Vt, right? Then it means you are having channel is created for the conduction from source to drain, right? And the more voltage, the VGS is more than Vt, how much more is called the overdrive voltage, right? So now if you increase your Vd from, let's say, same, taking same to source and then decrease it, then if that Vd, the distance between source and drain, the voltage between source and drain, if less than VOV, then you are in the triode region, and if it is equal to or greater than VOV, then you are in the saturation region, right? Even if you increase D more, you would be in the saturation region, right? So it means this distance and this distance will be equal, right? Because if VDS is equal to VOV, we are in the boundary of the triode, and this, and VOV is what? The difference between VGS and VT, right? So if you understood these things, right? So remember the voltage levels, right? So it means if you set your S ground here, VG would be in positive value, right? For example, if you put your ground G as ground, then your source would be negative to have these distances, right? Same is here. If you put your source to a positive value, then your gate would be lower than that, right? If you put your source at 0, your gate would be lower than, in the negative side of that, right? So now this is the curve obtaining equation. Here the polarities are fine, right? And you are having a curve here. Obviously VSD, not VDS. VSD is increasing, it means you are in the right side, right? But because this drain current is leaving, it means you must be having a negative sign here to plot it on the first axis, otherwise it would be on the third axis. So same, if VSG is now not greater than, is actually less than the absolute value, obviously it would be negative. So if you put magnitude, then you need to have a less than point, right? So if it is less than, how much less than? If much less than VTN, then how much less than? The difference between that would be the VOV. And now if VSD is less than VOV, you are in the triode region, right? Less than this magnitude of VOV. To avoid the sign, we use magnitude sign, right? If VSD is less than VOV, you are in the triode region. The same formula works, but with these, because VTP usually in negative sign, you need to put here, because in formula we already have a proper sign. If VSD is greater than or equal to VOV, you are now in the saturation region. Okay. So large signal equivalent circuit with early effect. This was an N-channel MOSFET without early effect, right? Introduced previously. How about the P-channel MOSFET? I told you, you have to do it yourself, right? And how about N-channel MOSFET with early effect? You are having an R out. And R out is equal to what? VA by ID, right? So incorporating the output is